5.4 to 6, Eigenvalues and the Dynamical Systems from Linear Algebra. Real eigenvalues. Example 1. A stretch of desert in northwestern Mexico is populated mainly by two species of animals, coyotes and roadrunners. We wish to model the populations C of t and R of t of coyotes and roadrunners t years from now, if the current populations C naught and R naught are known. From this habitat, the following equations model the transformation of this system from 1 year to the next, from time t to time t plus 1. C of t plus 1 equals 0.86 C of t plus 0.08 R of t, and R of t plus 1 equals negative 0.12 C of t plus 1.14 R of t. Notice that the coyote population goes up in part based on the number of coyotes that there are, but also in part based on the number of roadrunners, whereas the roadrunner population decreases as the number of coyotes increases and increases based on the population of roadrunners. So we want to begin by writing this as a matrix product. X of t plus 1 equals A times X of t. That would be X of t plus 1 equals A times X of t. So again, current year and next year. Notice that what we're given is a linear combination, and so we can write this as follows, that X of t plus 1 equals C of t plus 1, R of t plus 1, which would be the same thing as the transformation matrix 0.86, 0.08, negative 0.12, and 1.14 times the vector C of t, R of t. We call this vector X of t the state vector because it gives us the state of the system at time equals t, and we call X of 0 the initial state vector. Notice that sometimes instead of writing X of 0, we will just simply write X naught. This linear transformation is an example of what's called a dynamical system. It's dynamical because it's changing. It's a system because we're looking at the roadrunners and the coyotes and how they work together kind of as a whole system within this population. Suppose we begin with 100 coyotes and 300 roadrunners. Find a closed form formula for C of t and R of t. So to do this, we're going to do a little exploration. So we're going to start by exploring. So we have our formula. We have that X of t is given by that same matrix from above, 0.86, 0.08, negative 0.12, and 1.14 times 100, 300. And the 100, 300, because this is the X naught, Y naught that we're given. Pardon me, this is the C naught, R naught, which forms X naught that we're given. So when we do the multiplication, we're going to get 0.86 times 100 plus 0.08 times 300, which is 110. And negative 0.12 times 100 plus 1.14 times 300, which is 330. And what I want you to notice is that this is 1.1 times the initial state, 100, 300. We've got a name for these things, as I'm sure you recall. this 1.1, this would be our eigenvalue. Lambda, and it has corresponding eigenvector 100, 300. So here's our eigenvector. So together, these things tell us that x of t is equal to a to the t times x naught. Like that's just sort of known altogether. But we know since our x naught is an eigenvalue, we know that this would be equal to 1.1 raised to the tth power times that initial state of 100, 300. Come in.
It's about DC.
Mhm.
So for the documentary, I would like to see if I can interview great grandma. Do you think that is possible? Or who should I contact? Like, I have no idea what the schedule is going to look like, which I feel like is probably the biggest constraint.
I think that I don't know that that's going to be possible, not because of schedule. I don't think it's going to be possible because for memory.
Yeah.
So, but I do think you'll be able to get, like, I do think that it wouldn't take you that long to get some good footage of her interactions. So I think you could probably do some just informal
What
interviews.
about the interview do you think that would be like not possible with her memory?
Let me pause this since it's recording. Just to make sure that you're tracking what's going on. So if we said a to the t times x naught, this would be like saying a times a times a times da 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 times a t times x naught. This first one, because x naught is an eigenvalue, would be lambda times x naught. And then you hit the next a. So then this would be equal to a times da 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 times a. Now there's t minus one of them. The lambda is just a constant. So you're going to get a times da 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 times a. But now you've got a lambda squared x naught. So that's why we will have, when all said and done, here you had a lambda, here you have a lambda squared. Here you're going to have a lambda to the t times that x naught. So that's why that is showing up the way I'm claiming it's showing up. And if we just want to find c of t and r of t, we would get that c of t equals 100 times 1.1 to the t, and r of t equals 300 times 1.1 to the t. And so those would be my closed form formulas for c of t and r of t. Closed form as in I could just give you the t and you can spit out an answer. C. Suppose we have c naught equals 200 and r naught equals 100. Find x of t. Basically the same question, just in a different initial state vector. So once again, we're going to explore. So we have our same transition matrix, 0.86, 0.08, negative 0.12, 1.14. We multiply by our initial state, which is 200, 100. Notice this means we're starting with twice as many coyotes as roadrunners, right? Twice as many predators as there are prey. And it's not going to come as a surprise that when you multiply this out, you're going to get 180 and 90, which would be 0.9 times that initial state of 200, 100. So again, here's your eigenvalue lambda, and here is your eigenvector, your second eigenvector. So this tells us that our x of t with this particular initial state would be 0.9 to the t times 200, 100. Or if you wanted the closed form versions of c of t and r of t, you'd get that c of t equals 0.9 to the t times 200, and r of t equals 0.9 to the t times 100. D. Suppose we have C naught equal to R naught equal to 1000. Find x of t. And there's a hint, we're going to write x naught in terms of the eigenbasis. Remember, our eigenbasis is 100, 300, and also 200, 100. So we can do a little bit of math, and we learn that 1000, 1000, that initial state, is equal to 2 times 100, 300 plus 4 times 200, 100. We'll call this first vector b1, second vector b2. Okay. So we know that our x of t is equal to a of t times 1000, 1000. But this would be equal to a to the tth power times 2b1 plus 4b2, which would be the same thing as 2 a to the t b1 plus 4 a to the t b2. And remember, what kind of vectors are b1 and b2? Those are our eigenvectors. Okay. So from this, we get that a to the t times b would be 2. B1 has associated eigenvalue of 1.1. So we'll get 1.1 to the t times b1 plus 4 times 0.9 to the t times b2. Or in other words, our x of t has a closed form of 2 times 1.1 to the t times 100, 300 plus 4 times 0.9 to the t times 200, 100. We can continue on and sketch a phase portrait to describe this system. So phase portrait is as follows. So those of you that have had differential equations will find this pretty straightforward. For others, it'll be new. So we'll put our C's along the horizontal and our R's along the vertical. And then we'll graph the two eigenvectors. So we have the 200, 100, 200, 100. So here's a line formed by the B2 eigenvector. And remember, our eigenvalue there is 0.9. So if we start with something on that line, we're going to get smaller. And then our other eigenvector is 100, 300. Here's our B1. me see if I can move this over. So here's B2. So B2 is here. And the reason the arrow is pointing in is because that eigenvalue is a 0.9. And so making things smaller when you multiply by something on the B2 axis. And then B1 is here. This, and we can just continue the line. Here, our eigenvalue is 1.1. So if we start with something along that axis, we get bigger, which is why the arrows are pointing out. Let me see if I can make that clear. So this arrow is pointing in, and the reason it's pointing in is because lambda 2 is equal to 0.9, which is less than 1. So things are getting smaller. That's why these arrows are pointing in. And our second eigenvalue, or I guess it's our first, I did these in the reverse order, but lambda 1 was equal to 1.1, which is bigger than 1. And since it's bigger than 1, what color haven't I used? Since it's bigger than 1, we're going to end up with expansion along that particular path. So these are kind of our main main directions that we have to track in our phase portrait. And then what we're going to come through and do is we're going to say, if we started with some other initial state, what would happen? And so if we started at this point right here, notice that the pink arrows seem to be dominant, and so it's going to draw us in. But then at some point, the green arrows are going to become dominant, and we will take off towards along the B1 line. Similarly, we could sketch it in the other areas. So our phase portrait looks something like this. This is what's called a phase portrait. Notice that in terms of reality, which sort of counts and is sort of important. So note, only the first quadrant makes sense. At least makes sense with roadrunners and coyotes. The math doesn't care. Makes sense with roadrunners and coyotes. Okay. So for this particular question, you could even come through, and if you will, you could say, well, we don't actually care about anything outside that first quadrant, including the axes. That sort of makes sense in this context, that all we care about is the first quadrant, but again, the concept of a phase portrait makes sense everywhere else. Just to make it clear what that would look like, what we're saying is that if you started with lots of coyotes and few roadrunners, then both populations would quickly go to 0. If you started with roadrunners and no coyotes, then the roadrunner population is going to grow without bound. So that's kind of what it means to just get rid of the other quadrants in the context of the question. Here's another example. Consider A equal to 0.5, 0.25, 0.5, 0.75. Since the sum of each column is 1, this linear transformation is called a transition matrix. I believe I used this phrase on the previous example, but it wasn't actually a transition matrix because the sum of each column was not 1. So my apologies for that. We want to find a closed form expression for a to the t. Hint, since A is a transition matrix, one of its eigenvalues will be 1. So if we want to do this, the first step is to find the eigenvalues. So to do that, we need to find where the determinant of a certain matrix is 0. So we need to solve 0 equals the determinant of 0.5 minus lambda, 0.25, 0.25, sorry, 0.5, and 0.75 minus lambda. This is equal to a half minus lambda times 3/4 minus lambda minus 1/8. Of course, this is all equal to 0. And we could multiply all the stuff out, and we would get lambda squared minus 5/4 lambda plus 1/4. Again, this is all equal to 0. We continued on. This is telling us that 0 is equal to 1/4 times 4 lambda squared minus 5 lambda plus 1. Or I guess we can drop the 1/4, multiply both sides by 4. So we've got lambda minus 1 times 4 lambda minus 1, which tells us that lambda equals 1 and lambda equals 1/4. I guess this is be an or, not an and. Once again, notice the lambda equals 1. Here's the eigenvalue is 1. That tells us that we have a transition matrix like we were talking about. So next up, we need to find the eigenvectors. Okay, so we want to find our eigenvectors. So we start with lambda equals 1. And when we start with lambda equals 1, we've got to set up the matrix A minus lambda I. So I got minus 0.5 and 0.5 and 0.25 and negative 0.25. And you can notice here that if you had 1 of the first column and you had 2 of the second column, that the linear combination would be 0. And so that tells us that our eigenvector, our first eigenvector, will be 1, 2. Similarly, if lambda equals 1/4, then A minus lambda I would be 0.25 and 0.5 and 0.25 and 0.5. And here we notice that if we had 1 of the first column and we had, or if we had maybe negative 1 of the first column and 1 of the second column, then the linear combination would add to 0. So that tells us that our second eigenvalue is negative 1, 1. Notice that I was able to find the kernel just by inspection in these particular cases. Okay, so what does that do? Then what we're going to do is we're going to set up a change of basis matrix. So I guess you could say a 3 here is we want to change coordinates so x is in terms of the eigenvector, in terms of the eigenvectors. Oh, wait. maybe we could give these things names. If we called this vector right here B1, and this vector here B2. So we're saying our eigenbasis, if you will, is going to be B1 and B2. So our PB matrix that goes from the basis with respect to the eigenvectors back to the standard basis would be something like 1, 2, -1, 1. So these are coming from the eigenvectors, and we know what the transformation is going to do. So we have some transformation matrix and transition matrix. With respect to these is D equal to, and here we're going to take advantage of the eigenvalues that we already know. So remember, we had these eigenvalues, 1 and 1/4. And so we'll get a 1 and a 1/4 that are coming out. And it's a diagonal matrix. And what I want you to notice here is that the first column of the PB matrix corresponds to the first column of the D matrix. And the second column of the PB matrix corresponds to the second column of the D matrix. So notice that we can put these things together and we can say that our a to the teeth power, so this is kind of the fourth thing we're doing, a to the t would be equal to the p, now it's a d, p inverse, but it's all raised to the teeth power. And we know how that collapses. So this will collapse into just a p d to the t p inverse. And D is a diagonal matrix. And so taking a diagonal matrix to the teeth power is the same as taking the entries to the teeth power. And so this would be telling us that we have a to the t equals p times 1 to the t 0, 0, 1/4 to the t times p inverse. But notice that 1 to the t is simply 1. And so we don't even need the teeth power there on the 1. So because this was a transition matrix, an eigenvalue of 1, because we were able to diagonalize this time, because we're able to diagonalize, I guess that's where we're going to. The a to the t is really easy to write down. All right, let's continue on. All right, so we did all that to find a to the t, and now we're going to take on part B. So if x naught equals 1, 0, find a to the t x naught. So to do this, I'm going to sort of work backwards. So if I want to find a to the t times x naught, this would be like saying p, my d to the t, so that'd be 1, 0, 0, 1/4 to the t times the p inverse. And so times 1, 0. So I'm going to start by focusing in on these terms, the p naught times 1, 0. And we have the p inverse, which is 1 over the determinant, so 1/3 times 1, 1, -2, 1 times the 1, 0 equals, and let's pull a 1/3 out front. So we still have a 1/3. And so I'd have 1 times 1 plus 1 times 0 is 1. Negative 2 times 1 plus 1 times 0 is negative 2. So we get that the P inverse times 1, 0 ends up being equal to 1/3 negative 2/3. Continuing on, this tells us that our a to the t times x naught is equal to P times 1, 0, 0, 1 over 4t times, we could pull the 1/3 out front, so times 1 negative 2. Now we could try to figure out what is this blue expression equal to. So in that blue expression, 1, 0, 0, 1 over 4t times 1 negative 2 is equal to, let's see. So I've got 1 and looks like negative 2 over 4 to the t. Something like that. And that would be what our blue quantity is equal to, which tells us that our a to the t x naught is equal to 1/3 times p. And our p is the 1 minus 1, 2, 1 that we started with, times this garbage right here, which is 1 minus 2 over 4t, which would be equal to 1 over 3 out front times, let's see, it looks like we've got 1 plus 2 times 1 over 4 to the t. And in the denominator, we have 2 minus 2 times 1 over 4 to the t. And this whole expression would be a to the t times x naught. That's our closed form expression for a to the t times x naught. In part C, we want to find the steady state or the equilibrium vector. So to do that, we're going to find x equa, which is equal to the limit as t goes to infinity of this thing that we just found before. So 1 over 3 times 1 plus 2 times 1 over 4 to the t, 2 minus 2 times 1 over 4 to the t. And shockingly enough, the 1 over 4 to the t's are going to go to 0, going to go to 0, and we're going to be left with just 1/3, 2/3. Notice that the sum of the components still adds up to 1 because this is a transition matrix. All the columns sum to 1.